We'll do a strain transformation problem here. I'm going to use Moore's circle. Go ahead and read the problem statement. So it talks about a thin plate at the surface of the plate, and it says that surface is unstressed. So this is a plane stress problem. So sigma zz is equal to 0, and epsilon zz must be calculated. Right? It's free to move, this free surface. Right? Epsilon z is able to move because sigma zz is equal to 0. So here is the strain state given to you in equation format, and there's Poisson's ratio, which we're going to end up using. So let's go ahead and draw the strain state. Put our axes on, x, y. On the x face, we're going to draw arrow going in of 260. Y face, a smaller one, going in of 60. On the x face, in the y direction, because we've got positive, draw our shear strain, which is 480, and draw all the rest of the arrows. So we can get onto Moore's circle here. There's our canvas below. We've got normal strain on the horizontal, shear strain on the vertical. Clockwise is positive. So the x face is going to have minus 260 normal strain and minus 480 over 2. Right, go ahead and look at the x face right here. There's the shear strain. It would cause the element to rotate counterclockwise. Since clockwise is positive, that'll end up being negative. On the y face, we've got negative 60, and the exact opposite of 480 divided by 2. So let's go ahead and plot those 2 points, and then we'll be off and running here. So the x point is going to be at minus 260, about right there, and minus 240, so somewhere right about down there. That'll be the x point. Go ahead and label it minus 260 minus 240. The y point is going to be at about minus 60, 240. So we'll go ahead and label that right there. That's the y point, minus 60 plus 240. Very nice. We're just going to connect those 2 points. Off and running. All we need is the center. And we would also be interested in the radius. With that, we can solve for, that is a horrible looking circle, but we'd be able to solve for an epsilon. A principal. The question would wonder is, where is epsilon zz? We're going to have to calculate it. We'll do that in just a minute. So the center of that circle, go ahead and add the 2 normal strains, divide by 2. So the center is going to be at minus 160. That's good. We got a chance to now do R a little better. We go from minus 160 to minus 60. That's going to give us a total length of 100 and a height of 240. So our R squared calculation gives us an R of 260. So quickly we can get out our maximum normal strains. Epsilon max, epsilon minimum. So the way we're going to calculate the strain in the z direction is we'll look at creating it from the equation sheet. So epsilon zz, which is going to be equal to, from Hooke's law, right, a combination of the stresses, which we don't know, but we do know a bunch of strains. So what we're going to end up doing is looking at the inverted relationship, stress to strain as opposed to above, where we're looking at strain over to all the stresses. So the stress in the z direction, so this would be off the linear elasticity portion of your equation sheet. So sigma zz is equal to Lemay's constant times epsilon xx plus another Lemay's constant epsilon yy plus Lemay's plus 2 times g, again on your equation sheet, times epsilon zz. And we know that in a plane stress problem, that's equal to 0. So we're going to solve this equation for epsilon zz, and we're just going to do a little simplifying. So the strain in the z direction can be calculated if you knew the strain in the x and the y direction, which we know from the initial strain state. So we've just got a little bit of math to get through here. So I'm going to take and factor out on the bottom a Lemay's constant down there. That'll cause us to cancel. Let's take a closer look then on the bottom of 2 mu divided by Lemay's constant. So if we just use the definition for Lemay's constant and plugging in, we also have, there's our expression for g as a function of E and Poisson's ratio. So we just got a little bit of math to take care of, and we end up simplifying all the way down to 1 minus 2 Poisson's ratio divided by Poisson's ratio. So if we go ahead and plug that back into the 1 plus 2 mu over Lemay's constant, we end up with 1 minus Poisson's ratio over Poisson's ratio. So don't know if you'll have to end up doing that or not. It is doable on the equation sheet, but then you can solve for the strain in the z direction using only Poisson's ratio and the strains in the other 2 directions, in this case x and y. So we can go ahead and calculate the strain in the z direction. In this case ends up being plus 160, and so that ends up being the epsilon 1. That's the biggest, the most positive strain. 2 would be 100, and then epsilon 3 would be minus 420. So we'll also go through just drawing the rotated strain state at principal. So there's our initial strain state. There's the center of the circle, the radius of the circle. So to do this, we're going to end up using a pink theta again. So there will be our initial angle. We'll end up calculating it using an inverse tangent. We use 240 over 100. That gives us the pink theta, a value of about 67.4 degrees. Just one more quick look at that, right? That side would be 100. That would be 240. So there's how we're going to end up running our inverse tangent. Now we're going to end up with rotating to theta p. So we've got 2 ways to do that. We can take the x point and we can go to epsilon maximum in plane. That would be 2 theta p. Or we can take it and go the other way. That would be 2 theta p as well. So we'll start our theta games. We'll have 2 options. 2 theta p would equal theta, and that would be going in the clockwise direction. Or we'd end up with 2 theta p plus the pink theta. There's our 2 theta p, pink theta. That total strike is going to be 180 degrees. Plug in numbers, and we've got our answer for our 2 theta p's. And so that we're going to try to get the exact same answer whichever direction we go. So let's take a closer look at the first one. So when we rotate 33.7 degrees, now the x prime axis is down 33.7 degrees. Go back up to Moore's circle. So the x point is now sitting here. So on the x prime face would be epsilon minimum. So let's go ahead and put that on. That would be the minus 240, or sorry, minus 420. On the other face, we've got positive 100. So let's kind of go back up over here. Right, that point, as it moved over here, then the y point moved down and is now sitting right there. If we do it the other way, you end up with the exact same answer, rotating in the counterclockwise direction. Now the x prime axis is sitting up in the air 56.3 degrees. So it would be all the way over to epsilon max in plane, which is the 100. And then in the opposite direction, we've got 420. So again, we have to get the exact same picture, which we do, whether or not we rotate in the clockwise direction or in the counterclockwise direction. We only have one answer that we can get at principal strains. So let's do it one more time for theta s. We're going to take the strain state and we want to orient it up and down, straight up and down. So we're going to do that by striking through 2 theta s. So we can go 2 theta s. We'll just go the short direction here. That would put us y prime up here, x prime down there. And we've just got a little bit of theta, quick theta games here. So the pink theta plus 2 theta s is equal to 90 degrees, right? There's our pink theta sitting right there, plus 2 theta s is 90. So answer for theta s, 16.3 degrees counterclockwise. So if we go ahead and label that, all the stresses, we'd end up with 16.3 degrees. We'd have on all faces, we'd have epsilon average, which is at the middle of the circle. So you see 160 on all 4 faces. Right, on the x prime face, we'd be down here in the negative shear strain. Negative would be in the counterclockwise direction. So on that face, we're going to draw the shear strain, causing the element to rotate counterclockwise. Draw one, we can draw them all, and the shear strain is twice the radius because the vertical axis is gamma over 2.